probability of an impossible event. Obviously, impossible event is nothing but an empty set which does not contain any outcomes and hence its value is equal to 0. Probability of a complement event, that is not A, is always 1 minus P of A, or we can say probability of A plus probability of A dash is equal to 1. When two events will not have an intersection with each other, if they are disjoint, then they are called as mutually exclusive. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Department of Mathematics. So last session we have learned about the probability of certain events. Now we will learn about how to measure the probability of those events which we have learned earlier. So in this session we will learn the definition of probability through axiomatic approach. Also we will find the probability of certain random experiments. Axiomatic approach of probability. So let S be the sample space of a random experiment. The probability P is a real valued function whose domain is the power set of S and range in the interval 0, 1, satisfying the following axioms. So the first axiom says, for any event, the probability of an event E is always greater than or equal to 0. The second one says, probability of the sample space is equal to 1. And if E and F are mutually exclusive events, probability of E union F can be written as sum of probability of E plus probability of F. So from these definition, we can say the probability value always lies between 0 and 1. So either it can be equal to 0 or it can be equal to 1, but the value of the probability cannot exceed 1. So therefore, clearly from the definitions here, probability value of any experiment, of any event will always lies between the value 0 and 1, and 0 is for impossible event and S is for the sample space, that is for the sure event. The remaining all probabilities will have you the values less than 1. And the other thing is, if E and F are mutually exclusive events, when I say mutually exclusive, that is intersection of these two events is clearly empty, then the total probability can be written as the sum of individual probabilities. So this approach of learning the definition of probability value is nothing but the axiomatic approach. So from the definitions we have learned here, we have the following things to remember. Probability of a sure event is equal to 1 because the sample space probability is 1. And we know that sure event nothing but the event which is equal to the sample space. So therefore, its value is always equal to 1. And probability of an impossible event. Obviously, impossible event is nothing but an empty set which does not contain any outcomes and hence its value is equal to 0. Thus, we can say probability of an empty set is 0. And suppose S is a sample space which contains omega 1, omega 2, omega n, which are the outcomes, then probability of omega 1, probability of omega 2 plus probability of omega n will be equal to 1, which means there may be an event which contains only omega 1 as an outcome, there may be an event which contains only omega 2 as an outcome, similarly omega 1 as an outcome, which all are simple events. So when you add the probability of all those simple events, the total value will be always equal to 1 and hence the value of the probability can never be greater than 1. So the maximum value it can take is 1 and the minimum value is 0. The rest of the probability will lie between 0 to 1. Probability of equally likely outcomes. If the chance of occurrence of each simple event is same. So when I say probability of getting head when a coin is chosen is 50%, that is 1 by 2. Similarly, when a tail, that is also 50%. So when they are equally likely distributed with the probability value, we call them as equally likely outcomes. Now, the probability numerically can be calculated as probability of an event E, which is equal to number of outcomes favorable to E. That means number of outcomes in an event E divided by total possible outcomes, that is number of elements in S. So, and that number of elements in E is denoted by small m, number of elements in S is denoted by small n, and hence it is always m by n. We know that E is always subset of sample space, and hence the numerator contains the less value than the denominator, and hence the probability value is always less than or equal to 1. Now we will learn how do we assign the probability of certain events. The first one is probability of an event A or B. The probability of an event A or B is same as with respect to the cardinality of sets. So there we have learnt N of A union B is equal to N of A plus N of B minus N of A intersection B. Similarly, here also the probability value is taken in the form of probability of A plus probability of B minus probability of A intersection B. Now if suppose this term is 0, when we get this term as 0, when A intersection B is empty, that is, when A and B are mutually exclusive event, the probability of an event will become 0 because it's an empty set and the value of a probability empty is 0. So whenever it is 0, so the probability of A union B is just P of A plus P of B, or for any mutually exclusive events. So this is the definition for probability of A union B. Next one, the probability of the event not A. So not A is nothing but complement. So we know that A is nothing but, A dash is nothing but S minus A. So obviously probability of A dash is probability of sample space minus probability of A. We know that probability of a sample space is always 1. So it is 1 minus P of A. So since the value of the probability maximum is 1, so the complement value should be always 1 minus the given event. So therefore, probability of a complement event, that is not A, is always 1 minus P of A. Or we can say probability of A plus probability of A dash is equal to 1. Next one, since A and A dash are mutually exclusive and exhaustive events. Why we say mutually exclusive? Because any element in A will not be present in A dash because it's complementary to each other. So therefore, A intersection A dash is empty. Also, when you take the union of them, that is equal to the sample space. We have learned when two events will not have an intersection with each other, if they are disjoint, then they are called as mutually exclusive. And when the union of those events will get as the total sample space, they are called as exhaustive event. Here A and A dash are both mutually exclusive as well as exhaustive events. And hence here, probability of A intersection A dash will be equal to empty. So therefore, probability value is equal to 0. Similarly, probability value of A union A dash is the probability of a sample space, and probability of a sample space is 1. Next one, probability of the event A minus B. When I say A minus B, only in A, not in B. So that means if there are any common elements, we need to remove them. So therefore, probability of A minus B can be written as probability of A minus probability of A intersection B. We need to remove A intersection B from A. So therefore, when you apply the probability, it gives you the same formula. Similarly, if you want probability of B minus A, then it is probability of B minus probability of A intersection B. So this is how we will calculate the probability of different types of events. So now let us calculate the probability for different experiments. A die is rolled. Let A be the event, die shows 4, and F be the event, die shows even number. Are E and F mutually exclusive? That means whether E intersection F is empty. So first let us write the sample space when a die is rolled. So the sample space is 1, 2, 3, 4, 5, 6. Next, E be the event, die shows 4. So only possibility is 4. It's a simple event. F be the event, die shows an even number. So that is 2, 4, 6. So here E intersection F is 4. This is not equal to empty. So therefore, they are not mutually exclusive events. I'll write here in the form of MEE. So it is not mutually exclusive events because they are not disjoint. Next one, 3 coins tossed once. Let A denotes 3 heads show, B denote 2 heads and 1 tail show, C denote the event 3 tail show. and D denote a head shows on the first coin. Which events are mutually exclusive, simple, compound? First, let us write the events. Event A, here 3 coins tossed means the sample space will be H, 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 T, H, T, H, T, H, H, T, T, H, T, H, T, H, T, 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 T. So there will be 8 outcomes. Now A denotes 3 head show. So 3 head show means the only thing is H, H, H. Next we'll take B. Event B says 2 heads and 1 tail. 2 heads and 1 tail means HHT, THH, HTH. C denotes 3 tail show. So T, T, T. D denotes a head shows on the first coin. So that is H, H, H. First coin head means H, H, T, H, T, H, then H, T, T. So from the sample space, you can derive all these sets. Now they're asking us, the first one is mutually exclusive. Which events are mutually exclusive? Now check A intersection B. Do we have any common elements? No. So this is equal to empty. So therefore they are mutually exclusive. Next, A intersection C. It is also empty. A intersection D, not possible because we have H, H, H. Check B intersection C. B intersection C is possible. B intersection D, no. We have a common outcome here. Check C intersection D. Yes, it is possible. So therefore, these pairwise events are disjoint and hence they are mutually exclusive. Next one, how many of them are simple events? So the answer for the second, simple events means set A and set C, because they contain only one outcome. So therefore here A and C are simple events. Compound events means one is B, another one is D, because they have more than one outcomes. So therefore B and D. Next one, 2 dice are thrown. The events A, B and C as follows. A getting an even number on the first die, B getting an odd number on the first die, getting sum of numbers on the die less than or equal to 5. First, let us write the event A, B, C. So when 2 dice are rolled, we have a 36 outcomes. So let us write just event A, B, C instead of a sample space. So getting an even number on the first die means set A, so that is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Similarly, we get 4, 1, 2, 4, 6, 6, 1, 2, 6, 6. Next, event B is getting an odd number on the first die. So B 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Similarly, 3, 1, 2, 3, 6, 5, 1, 2, 5, 6. Next, event C, sum of number on the dice is less than 5. C, I can choose 1, 1, 1, 2, 1, 3, 1, 4. I cannot take 1, 5 because 1 plus 5 is 6. So which is greater than 5. So the next I can write is 2, 1, 2, 2, 2, 3. Next I can write 3, 1, 3, 2, 4, 1. So these are the outcomes which add up to 5 or less than 5. So we have written the events. So based on the events, we need to check the following statement. State true or false, give reason. A and B are mutually exclusive. So look here, event A contains only the outcomes which starts with even number. Event B contains only the events which starts only with 1, 3, 5. So none of the outcomes in A and B have common outcomes. So obviously they are mutually exclusive. So therefore it is, here we can say true because A intersection B is empty. Second statement says A and B are mutually exclusive and exhaustive. They are mutually exclusive? Yes, true according to the first statement. Exhaustive means their union should be equal to sample space, and yes, they are equal to the sample space because here A contains all the outcomes other than the outcomes in B, and when you take the union of these two, you will get all 36 outcomes of the experiment, and hence they are mutually exclusive as well as exhaustive. Is A is equal to B dash? That means whether it is a complement of B, check. Getting an event number on the first die. So getting an even number on the first die means the complement of A dash or A dash should be getting an odd number on the first die. Obviously, B is getting an odd number on the first die and the complement of B is getting an even number on the first die. So obviously, B dash is equal to A. So therefore, the statement is true. Next, A and C are mutually exclusive. So we need to check here whether A intersection C is empty. Let's check. So here we have events 2, 1, 2, 2, 4, 1 are common. That means A and C contain some common elements. They are not disjoint. So therefore we can write here false because their intersection is not empty. Next, let's take few more problems. One card is drawn from a well-shuffled deck of cards. If each outcome is equally likely, calculate the probability of the card will be a diamond, not an ace, a black card, not a diamond, not a black card. First one, let me consider it as an event A. So, when we have a deck of cards, we know there will be 52 cards. So these 52 cards have 4 more subdivision. So one is diamond, another one is heart, next we have club, and the other one is spade. And in that, diamond and red are red in color, club and spade are in black color. So each division contains a number from 1, 2, 3 till 10, and then we have jack, queen and king. So now 13 cards, 13 hearts, 13 clubs, 13 spades will give you the total cards of 52. So when we are deciding here about the event, so we need to check the favorable outcome for the event because probability is always number of favorable outcomes divided by its total number of outcomes. And the total number of outcomes for this experiment is 52 because there are 52 cards. Now first experiment is, I need to calculate the probability of choosing a diamond. So when I say diamond, I have 13 diamond cards. So therefore, number of outcomes for the event A is 13. So therefore, the probability of an event A is 13 divided by 52, which is equal to 1 by 4. Next we have not an ace. We have 4 ace here. So 1 is nothing but ace. So A is in diamond, A is in heart, club also contains ace and spade. So all cards from A to K. So we have 4 ace. When I say not an ace, this is obviously 52 minus 4, which is equal to 48. So if I take B as an event which contains not an ace, then the number of elements in B is 48. So therefore, the probability of an event B is favorable outcome divided by total outcomes. So this value will be equal to 12 by 13 divided by 4. Next one, a black cards. So see here, we have a black cards which are club as well as spade. So 13 club, 13 spade, which is equal to 26. So therefore here we have 26 black cards, and hence if I consider event as C, number of cards in C is 26. So that means we have 26 black card. So probability of C will be equal to 26 by 52, which is equal to 1 by 2. Next question, we have not a diamond. We have a diamond, we need not a diamond. So it's complementary to each other. So therefore we know the probability of a diamond, we got it as 1 by 4. So let me write the event as probability of not a diamond. So when I say not a diamond, then this is equal to the complement of set A, because set A is a number of elements in diamond. So there are 13 diamond cards and its probability is 1 by 4, and here I am calculating the probability of not a diamond. So therefore this should be equal to 1 minus P of A, which is 1 minus 1 by 4, which is equal to 3 by 4. Or we can also calculate it in some other way. If I choose D as an event which is not a diamond, then so there are 13 hearts, 13 clubs, 13 spades which are not diamond. So therefore there will be 39 cards out of 52. So obviously the value is the same. So this is using the concept of complementary event. This is a direct calculation with m by n. Next question is, I need to calculate not a black card. Obviously when we say not a black card, they are red cards and there are 26 red cards. So if I choose it as an event E, then again it is 26 by 52, so which is equal to 1 by 2. So this is how we'll calculate the probability of a given favorable event. Next question, a bag contains 9 discs, which 4 are red, 3 are blue, 2 are yellow. The discs are similar in shape and size. A disc is drawn from the bag. Calculate the probability that will be red, yellow, blue, not blue, either red or blue. So there are 4 red, 3 blue, 2 yellow. So total there are 9 discs. So that means n value is 9. M changes according to the condition. The first one says it is red. So probability of getting red if I take, so there are 4 red, so the probability is 4 by 9. Next, yellow. So if I take B as an event of getting yellow, then the total probability is 2 by 9. Next, blue. If I consider it as probability of getting blue, then it is 3 by 9, which is equal to 1 by 3. Not blue. Not blue means complementary to blue, which is 1 minus 1 by 3. So any complementary should be subtracted from 1 because it is the total probability value. So which is equal to 2 by 3. Either red or blue. That means probability of red. Probability of red is taken as A. Blue is taken as C. It is union C. So obviously they are mutually exclusive because there is no intersection with the colors. So that is equal to probability of A plus probability of C, which is 4 by 9. So let's keep 3 by 9 only for easier calculation, which is equal to 7 by 9. Next one, a coin is tossed twice. What is the probability that at least one tail occurs? When a coin is tossed twice, the sample spaces H, 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 T, T, H, T, T. Let E be the event, at least one tail occurs. That is HT, TH and TT. So here N is equal to 4, M is equal to 3. Probability of an event E is M by N, which is 3 by 4. A die is thrown, find the probability of the event. So when a die is thrown, number of elements in the sample space is X. A prime number will appear. So let this be an event A. When I say prime number, it is 2, 3, 5. A number greater than or equal to 3 will appear. Let this be event B. So 3, 4, 5, 6. A number more than 6 will appear. So let it be event C. It is clearly empty. A number less than 6 will appear. So let this be D. So it is 1, 2, 3, 4, 5, 6. Now let's calculate the probability of A. Probability of A is 1, 2, 3. Favorable outcome is 3 by 6. So therefore it is 1 by 2. Let's calculate probability of B. So number of outcomes which are favorable is 4 divided by 6. So 2 by 3. Next C. Probability of C. There is nothing here. So it's clearly empty. Probability of an empty set is 0. Next event D. Probability of an event D here, which has 5 outcomes. So therefore this is 5 by 6. Next one. If 2 by 11 is the probability of an event, what is the probability of an event not A? We know that probability of an event not A is always 1 minus probability of A, and probability of A is 2 by 11. So it is 11 minus 2 by 11, which is equal to 9 by 11. Next one. Given P of A is equal to 3 by 5, P of B is equal to 1 by 5. Find P of A or B if A and B are mutually exclusive events. We know that probability of A or B is nothing but A union B. We know the formula, that is probability of A union B is probability of A plus probability of B minus probability of A intersection B. Given A and B are mutually exclusive. So they have already given A intersection B is empty. So then the probability of A intersection B value must be equal to 0. So therefore probability of A union B is equal to 3 by 5 plus 1 by 5 minus 0, which is equal to 4 by 5. Or directly we can write this formula instead of writing this, because clearly they have mentioned it as mutually exclusive, and hence keep it in mind that its value is 0. Just use this formula, we'll get the same answer. So today in this session we have learnt the definition of probability and calculated the probability value of certain events. I'll meet you in the next session. Until then, keep watching, keep learning and keep exploring. Thank you.